About an honor board to wear at graduation.
So last time was how to integrate a function just over a rectangle. So we're going to go a little bit beyond that. All right. So the idea is this. We have a region D that is not a rectangle, and we want to compute this double integral over it. So say the region looks something like this. Then what we do is we define a rectangle R that contains the region D, and then we can define this in terms of a double integral over R instead of this function, big F of xy, where we define big F to be equal to little f for any point that's actually in D. So here big F is equal to little f, and then outside it's equal to 0. So out here, big F is equal to 0, so that means that as we integrate over a rectangle, like we did before, that big F is out here is not going to make any contribution to the integral. So all we're going to get is what's part of little f, that's all that we want. Okay. So that just gives us a way of defining it in terms of something that we've already seen. But how do you go about actually computing integral like this using the same techniques that we know, using a fundamental theorem of calculus and so forth? We like to do this in terms of one-dimensional integrals, just like we did for rectangles. So there's certain regions for which we can do this. So say that D is a region of type 1, Roman numeral 1, if D consists of a set of all points so that x is between A and B, so it's bounded by two vertical lines, x equals A, x equals B, and bounded above and below by curves. Y is g1 of x, and bounded above by g2 of x. All right. So this is something we can handle using an iterated integral, because then it's a double integral. It's this integral from A to B. And then the inner integral, before we had limits C and D, constants. But now what we have are functions of x. g1 of x, g2 of x. So our inner integral, it has to be with respect to y, and then our outer integral is with respect to x. So whichever variable, x or y, has variable limits, that has to go on the inside. So it's not like with rectangles, where we have total flexibility, we can choose either order we want. Here, the type of region that we have constrains you in that regard. Now, so that's one type of region that we can do. Of x and y. You get another region that you can do. So we say D is a region of type 2. If D has a set of all points where y is bounded by constants, what you see in D, both bounded above and below by horizontal lines, and then the left and right boundaries are functions of x. x being a function of y. So x is bounded by h1 of y to the left, h2 of y to the right. So when you do your inner integral, whether it's a region of type 1 or type 2, right, so you're integrating with respect to x from a to b, for each x in between, you're performing a one-dimensional integral. Say this is x equals c. So your inner integral is going to be from g1 of c, whatever c is, to g2 of c. So you're just going to do your antidifferentiation in the same way. The only difference is when you plug in your limits, those will happen to be functions of x in this case, functions of y in this case. So here we have the outer integral with respect to y, inner integral with respect to x. So at least regions of those forms, not hard to handle using a iterated integral. Let's take a region that's going to be of type 1 and do an example with that. Suppose we have this region. It's bounded by x equals 0. X equals. Then we have y equal x. Then we have y equal x squared. And then, so this is our region D that I'm going to shade in here. Okay. So these intersect when x equals 0 and x equals 1. And our integrand, defined by function of z, function of x and y, that's going to be 8 minus x minus y. So it's a region bounded by, we'll draw this in free space. So we have this wedge. So that's D shaded where z is equal to 0. And then we have these surfaces. But the top of this object is defined by a plane. So that peaks at z is equal to 8, and it goes down from there. So it's this solid that's bound on top by this plane, and is shaped like this wedge all the way up. That's what the solid whose volume we're going to compute. So the volume is going to be this integral 0 to 1, and then you have to keep track of which of these functions is the one that's less. That's going to be the bottom function versus the other one being the top function. X squared, which is normally greater than x, is actually less than or equal to x on this interval. So that is the lower limit. X is the upper limit. And then fill in your integrand. Okay. So this is a region of type 1. Your inner integral with respect to y, the limits, okay, that's just to be a superscript, x squared, the limits of that integral are functions of x. Okay. So, now, we'll carry out the inner integral with respect to y. So we're going to have 8y minus xy minus y squared over 2, evaluated, what?
in the notes